but I think we're now ready to get this going. Over to you.
Perfect. So I guess it's all Avnish's show now, and I'll try to fill in wherever I possibly can help. So, hi guys, still here. You've already seen a lot of me, just sitting around for a bit. But yeah, so we'll just get quickly started with this thing. The idea around the deck, that I'm presenting today is to, get a hands-on feeling as to how we can actually go about building a public ledger. That's it. We might end up with a blockchain, but that's going to be incidental. What's more important is the journey, as they keep saying all the time. So, and along the journey, we are also going to explore different use cases and how each and every individual step in building the public ledger can actually give us different use cases. Okay, so what we're going to do is, is to try building the protocols around which public infrastructure might work, and see at each and every given step how, each of these protocols or steps can actually be utilized as full-blown business cases. So, yeah, next slide, please. Okay, so this is a pretty tried and Thakawa cartoon that I've been using for a fairly long time. It's one of my favorite strips, Dilbert. But I think this is still as relevant as the first time I used this around 3 years ago. We still pitch blockchain to large corporates or banks and C-suite people, and it still has the same let's just say a sense of non-recognition of tech. So what we are trying to do is to have a very gentle introduction to tech. We're not going to talk about servers or any coding, but we are going to try to build something logically. That's it. Next slide, please. Now, before we get started, I would want to, first of all, illustrate the differences that we should expect between a centralized and a decentralized system. So on the left, we have a totally centralized system, which is your typical three-tier architecture. You have the application service provider, which basically is the organization responsible for holding all the servers and the access to your data. And on the right, you have a purely decentralized network in which every single viable participant on the network has actual access to the data. And it's not just read access or maybe enough access to download and secure the data remotely. It's actual access at all times. So a good example of either of these would be on the left, it would be any of the large or cloud-based companies or any website that you visit. So from Google to any cooking blog, you have on the left a typical three-tier centralized architecture where you, as the consumer interacting with a site, are just a consumer. You don't actually have any rights to the data. Whereas on the right, you have a totally decentralized network. A good example would be the torrent networks, in which each and every participant is obviously called a peer because they both contribute to the network in terms of serving the data, and they are also the clients to the data, right? Because you can both download and upload data from the network, and you have full access to it at all times. Now, the difference between them would be much clearer as we keep going along. But yeah, enough talk about distributed and centralized system. Let's just see how if we were to build a public ledger today, how it would work, right? So next slide, please. Okay, so just to begin, previous slide. Yeah. So to begin, we are going to set some base rules. And these are very simple rules, right? So since it is a public ledger by default, and again, and this is a caveat for this talk because there are enterprise blockchains and then there are public blockchains, and enterprise blockchains are characterized by this fact that they are limited in the number of participants that can join, right? So right now we're only going to discuss public ledgers, but at the end of this talk, maybe we can bring up private ledgers as well and see how they might work and how they actually end up behaving differently as well. So to begin, if you want to have a public ledger, you need to set some base rules. And these are pretty simple base rules, right? So the first rule is pretty simple. Anybody can add a line to a ledger, which sounds pretty intuitive. And the second is you settle by netting. Okay, let's just see how this works in practice. Next slide, please. Next slide, Avnish. Okay. So I am going to take a sample scenario of 4 friends. So there's so we are in India, so obviously it's not Alice, Bob, Charlie. It has to be Amar, Akbar, Anthony. And then there's you. So these are 4 friends who decide to set up their own public ledger. Now, the first rule of this club was anybody can write their entries to the ledger, which is what we see on the left. So on the left, you have a ledger. This is like a typical ledger. People familiar with Tally would be very familiar with this kind of, okay, so this is not really a double entry, but you can even have a double entry ledger if you really prefer that way of accounting transactions. But yeah, a ledger is a ledger. So the first rule is anybody can write transactions to this, okay? And on the left, you have all the transactions. And on the right, it's actually pretty interesting because we see that Amar owes somebody $20. Akbar needs to get 10, Anthony owes 30, and you actually need to get paid 40. But who essentially is responsible for giving you this money? So, and what did we do here? So the only thing that we did here was to tally up all the transactions in the ledger, and we came up with the running balance of each and every single person. And the way we settle these transactions is by pooling cash to the netting center. And at the end of the period of accounting, okay, so once everybody has written the transactions to this public ledger, at the end of this accounting period, people settle their amounts or their ledgers through the netting center. So instead of you committing two transactions on the network, you end up getting only one transaction, and so on. So in a way, this is going to decrease the computational cost of running it. So whereas on the left, you see so many transactions, on the right, it's essentially just 4. So even if your ledger would have hundreds of transactions, you would effectively be able to settle all of them through 4 or 5 or whatever is the number of participants on the number or transactions. So that's a very powerful thought. And I think we can actually have a business case right away. Next slide, please. So we talked about tallying up transactions, and this is something which is used in practice all the time. People familiar with RTGS, which is a real-time gross settlement system used by a lot of payment networks, is something which does the same. So you have banks who have on-us and off-us transactions, and there's a single central, let's say, entity which is responsible for keeping a running tally of who owes whom what. And at the end of every netting period, people just take away money from the netting center, or they end up paying to the netting center. And this is something which is very useful if you're also running let's say a multinational company. So in a multinational setup, you would have multiple companies in different geographies, and a lot of the times your companies in different geographies have to talk to each other. When I say talk to each other, lend money to each other, or there are companies who actually owe some money or have to get paid by each other. So instead of incurring a fixed transaction fee for every single payment that has to go out, what you end up doing is keep a running tally of all the transactions for all the participants on the network on a managed ledger, and you decide on the netting period. So typically it's a quarter. So every 3 months or on every monthly basis, you are going to tally all the transactions that have happened, and then the netting center is then responsible for either paying the participants who need to get paid, or collect money from participants who have to pay others. So this is a pretty powerful business case, which ensures, and again, so the immediate uses or benefits of this use case are reduced FX costs. So if you need to do 4x transactions for every single payment, you can immediately bring them down by netting all those transactions into one. Okay, so we were able to get started with the public ledger. We now have a good way of recording transactions, and we also have a way of settling them. So what could go wrong? Next slide, please. Okay, the problem is Anthony. If any of you have actually watched the movie, you would know that Anthony is the problem child. And as we can already see, Anthony is wearing the topi, and the guy actually knows topi pehnana kaise padta hai. So what Anthony says, so what Anthony does with the ledger is he starts adding records. Because the ledger was open and there was no security, Anthony could actually tamper with the records and ensure that the records now show that everybody owes Anthony something, instead of Anthony actually ending up paying to the network. So we now need to ensure that in a totally public-private network, we have to find a way to ensure to have these bad actors disincentivized from doing it. And I think there's a very ingenious method for doing this. And it's called digital signatures. Next slide, please. Next slide. Okay, so the way we do this is actually pretty intuitive. In fact, you would do this every single time you would, sign an IOU. So what an IOU is, again, it's a receipt or a note for you owing somebody some amount of money or some asset. And every single time you do this, you are entering into a contract, which could be a bilateral contract or a multilateral contract. But you do this by signing against it. So you actually end up putting your own wet signatures against it. But since we are building a public ledger which has to be available over a network, we have to find a better way of doing it, because a wet signature can be tampered with. Anybody can change it, anybody can copy it, and it's not really that secure. Digital signatures, on the other hand, they really are. So consider a single transaction. So what we have here are two scenarios of two transactions, and we can also see that there are two functions. One function lets us sign the transactions, and the other lets us verify. Now, the cool thing here is that your sign function lets you consume the message that you want to encrypt or that you want to sign, and it consumes the secret key, which is available with you only. Okay, so this is a cryptographic secret key, which looks like a series of ones and zeros, and which only you have. Okay, and this function creates a signature. Now, since the function is consuming a message, this means that every single signature is unique. If the message is unique, then every single signature should also be unique. All right. In a way, this means that this means that instead of you only verifying somebody signing or wet document looking at the wet signature, you're actually considering the entire document along with the signature that we have put on it, which means this is actually a lot more secure way of doing it, because the act of binding your signatures to the document itself make it totally tamper-proof. Now, on the other hand, you have a verifying function as well, which consumes the message. It also consumes the signature that you want to verify, and it consumes a public key. Now, the public key is the publicly available component of the public-private key pair, which everybody has, unlike the secret key, which only the signing entity should have. And this verifying function returns either true or false. So if the message really did correspond to the signature which was sent, it would return a true, or else it will return a false message. Now, this might sound pretty complicated, but this is what we use every single time we browse a website. And every single time you see that there's a website which is HTTPS and it's secure, this is exactly what's happening behind the curtains. And like I said, since every single transaction uses a message and the secret key to get signed, it means that no two dislike messages can have the same signature, which is what you see in the illustration above. So you had a transaction which had a series of X's, and you had a transaction which had a series of O's. and either of those signatures would be different, even though they had the same secret key to sign them. Okay, so how does that protocol look now? Next slide, please. So we've added a new line to the protocol. We still know that anybody can add lines to the ledger. We know that we can settle the ledger by netting at the end of the netting period. But we added a new caveat or a new rider to the protocol, which means that only signed transactions are valid. So what does that make? Where does it land us? So the thing is, even with new lines coming in, anybody can still copy a transaction and then paste it, right? So all I have to do is, since I know what message, so let's just take, the transaction where Amar pays Akbar a sum of 30 rupees, and you have a signature against this. All Anthony has to do is copy this and then paste this to the ledger. Now we are going to prevent that by assigning unique transaction IDs against every single ledger entry. Now this is basic bookkeeping, right? This is what you do every single time you make a journal entry, right? So all we are saying is every single journal entry has to be unique, and the act of putting that unique transaction ID in that journal ensures that every single message is now unique as well. So if you look closely, every single transaction actually looks the same because it's eventually Amar paying Anthony a sum of 30 rupees. But the transactions, which you can see in blue, those signatures don't really look the same, which is true because the transaction IDs for each single transaction are unique. So this is one way for us to ensure that every single transaction is uniquely recorded and nobody can then copy and paste a previous transaction as well. So this is one way for us to ensure that even if people want to copy something, it will end up as a unique entry on the network every single time. Okay, so since we now have a ledger which works pretty well and you can uniquely add entries and nobody can then tamper with it, where does this land us? Next slide, please. Okay, I think the problem is still Anthony. So like I said, Anthony really was the problem child. I mean, he's a great guy, but once he really gets drunk, he starts spending money. Otherwise, he's a totally great guy. But once he starts spending, he also drinks and then he spends some more, and then he gets into a debt. And that's exactly what you see highlighted in the ledger above. So what you are seeing here is a series of transactions where Anthony is paying people in the network a lot of money, right? And if we were to continue in the same breath, ad nauseum, ad infinitum, this would end us up in a scenario where people would actually have to trust each other to get back their money. Okay, so we have to understand that at the end of the day, we are building a public ledger, and the public ledger has to have very strong governing principles. Now, what we are seeing here is probably a way for Anthony to sign off IOUs, but no way for the ledger itself to govern that Anthony cannot, sign a check that he cannot pay off eventually. Okay, so we then have to solve the problem of Anthony overspending. So let's see what the protocol looks like now. Next slide, please. So we already added the signed transactions protocol, and now we need to also ensure that there's no overspending in the network. Please also see that we are canceling out the nettings based settlement from the network. This is important because in a public ledger, if you settle every time through netting, during the netting period itself, again, in a public ledger only, and if the netting period is way too high, during the netting period, certain entities might accrue balances that they are unable to pay off eventually, right? So we need a more robust way of managing this expenditure and a more robust way of ensuring that the transactions are always following a logical pattern. So we now have three items in our rule book. Anybody can add lines to the ledger. we only allow signed transactions, and nobody can overspend. Let's see where this takes us. Okay, so the way you would end up building this is instead of people just adding transactions to the ledger, you would ask people to put some money on the pot. Okay, and this is exactly what the first 4 transactions are. It's just, you know, a bunch of people putting money into the pot there, right? And then once people have their available balances tallied up and visible to everybody on the network, we are then going to have a running tally or a running balance for each and every single participants. And let's see what happens. So we're just going to run the previous ledgers once again. So Anthony pays Akbar $40. Anthony's starting balance was $100. So now he has 60. So the running balance is 60. He then pays another $30. Okay. So there's $30 gone. So now the running balance is 30. Akbar pays you another $30. Okay. Anthony pays Akbar $10, which means Anthony has already spent $80 from the pot, which means that the running balance that Anthony is maintaining on the network is now 20 rupees only. And if you look at the 9th transaction, which is Anthony paying Amar a sum of 90 rupees, that's something which would immediately get qualified as invalid. So the network would not allow that to ever happen. Okay, so the protocols do not allow overspending because the rule book itself dictates that every single participant has a running balance calculated, and every single time they try to spend something which is way beyond their existing balance, they can't do it. Okay, let me make it very clear that this is true only of public blockchains. And even then, it is true only of a certain flavor of public blockchains. It doesn't have to be true with every single blockchain. It is true of public ledger that we are building. Okay. Okay. So one cool thing that this leads us to is after we've pooled an amount to the central ledger, we can keep a running balance on the ledger forever. We actually don't ever have to take money out of the ledger and spend it or give it to each other in cash, which means that once we have abstracted away fiat and made it available on the public ledger that we are now running, we can do any kind of transaction as long as we are well within the bounds of our balances, and we can keep adding balances as well, but we don't ever actually have to deal in real money. And this is pretty cool because a lot of companies have utilized this way of doing transactions in which, even though, let's say, a sum was paid in fiat money, they record that transaction in the same in a separate public ledger. And on the public ledger, they can start transacting with different entities without ever going through fiat again. And I think it calls for a use case now. Let's see the next slide. So trustless loans are something which follow pretty much the same pattern, because you can have borrowers who are essentially unbanked, and they would, again, so if there's somebody who's unbanked, it's a high possibility that they would not be reachable by any public ledger as well. So you might have lenders who lend to the borrowers through fiat only, and a collection and the collection transactions happen through fiat as well. But the act of recording that transaction can actually end up happening on your public ledger that you're building. And once the action is recorded on the public ledger, that running balance can then be utilized for multiple secondary transactions beyond that. So this is actually a use case that we built and were able to run in Southeast Asia. The idea, like I said, was again, take banking to the unbanked, ensure that lenders can lend to borrowers through either fiat or even cryptocurrency, and you can then have a series of transactions linked not to the fiat peg, but to a digital currency and available on a public ledger at all times. The network obviously also supports different entities to get enrolled as either data providers who will be able to provide useful, meaningful data to the lenders in order to run their models, credit rating models on top of them. And it also ensures that, if you want to run, let's say, a loan servicing agency, you can actually help the lenders with the loan servicing and then charge a fee for it. So this is actually an entire ecosystem based on the fact that once a single fiat transaction has happened, the entire series of transactions proceeding from that can actually end up getting recorded on a public ledger, and you don't ever have to transact in fiat again. We can probably talk about this later as well, but I think we can get back to the network. Next slide, please. So the one thing that we've left out is who really owns the ledger, because we've talked about people hosting this network and we've talked about people writing to this ledger, but where is the ledger? If we were to do this the way we currently do it, we would do it on Tally, or we would do it on Zoho, or we would do it in a spreadsheet. But all of those solutions are still centralized or available on a website or on somebody's server or on somebody's desktop, which means it's still not really public. And what we wanted to end up with was a totally public ledger. And what we're now seeing is everybody owning a database of sorts. But this leads us to a problem. And we'll see what the problem is in the next slide. Okay, so this is supposedly a light-hearted slide, but it's actually a very true problem. And the thing about networks is when everybody in the network has a copy of a ledger and they're going to be listening to all these transactions that are going to coming through from the dark, they're going to have no way to decide which transactions are actually supposed to come first, which transactions are supposed to come last. There are going to be network failures as well. Who's going to handle those failures? So we need to solve for this problem. And I think our protocol is now in serious need of another upgrade. So let's see how the protocol looks like now. Next slide, please. So we've already seen 3 rules written to the protocol. A 4th rule has to be found. We need to find a way to order transactions. And this is not an easily solved endeavor, because you're talking about multiple copies of a ledger and different owners of those systems listening for transactions. Some of those transactions may get dropped because of packet loss. Some of those transactions may reach late. And you now want to ensure that people can find a way to come to a consensus as to what the transactions are, A, and B, in which order did they arrive. I think I've already given the game away, because this is the one crucial secret sauce behind blockchain. So the protocol for ordering transactions is essentially what the consensus algorithms are all about. Now, since we are going to build a more Bitcoin-like public ledger, we'll try to arrive at a more proof-of-work-like consensus algorithms. But for different blockchain networks, they've found different ways of solving the problem, which essentially is, how do you order transactions? How do you know that transaction A came before transaction B, which came before transaction C, right? So there are different ways of solving this. In private permissioned way networks, you have different ways of solving this, and you have a totally different way of solving this for public networks as well. The one solution, the one consensus algorithm that we'll be focusing on for today's session is going to be proof of work. But you can always ping me up if you need more info about any of the consensus algorithms as well. Okay, so let's get started with the protocol for ordering transactions. Next slide, please. Okay, before we go any further, are there any questions? I know I've been spouting off for a very, very long time.
Sure. I've been looking at some of the questions that have come in. They are more general in terms of the concept of blockchain itself. I was thinking maybe if you'd like to finish this, I think your flow is going really well and you're really building on it. For example, questions such as what are the role of blockchain in financial services? How do you build a career in blockchain? Why is cryptocurrency being prohibited? And those are the kind of questions you've got. I haven't had a chance to look at the live chat, but I will also have a look at that. But I suggest we just keep going and then we can cover the questions at the end.
Perfect. All right.
Yeah.
So I guess I'll actually end up asking one of those questions right away. If you can just look at the figure up here, and if you want to build a career in blockchain, that's exactly your career over there. So what you have is expectations versus reality. I think that answers your question, and I won't have to answer that again. So before I talk about the consensus algorithm, let's just get one thing out of the way, which is the cryptographic hash function. Now, I know this might sound like a non sequitur because this has got nothing to do with consensus right away, and it's not really that intuitive, but just hear me out. So a cryptographic hash function is, again, it's a cryptographic function, obviously. It takes a message as an input. Okay, so it can be a message, it can be a file, it can be anything. So it takes an input and it spits out a digest of a fixed length. Okay, now, okay, so what's so great about it? What's great about it is while the digest or the output is of a fixed length, that output is unique to the input you gave in. In a way, you could say that a cryptographic hash function can be used to get the fingerprint of any message. So if you recall that every single message, when signed using a unique secret key, would reveal a unique signature. That's almost similar to how a hash function works, only that there's no secret key here. It's just a function itself, and it just consumes a message. And every message has a unique fingerprint against it. Okay, and that's all. That's all there is to it. Now, what you see in the pictorial representation is, I think, very pithy, because you might have a message which is multiples of MBs in size, but you will end up with a digest which is of a fixed length every single time. And it can be a 256-bit digest, it can be a 512-bit digest, depends entirely on which flavor of this hash function you've ended up using. Okay, so yeah, that's all the cryptography that I had to talk about. I think we can get back to building the consensus now. Okay. How we are going to use our newly revealed cryptographic hash function. So what you see here are essentially the ledgers. Okay, so you have three copies of the ledger, and you have transactions on each, right? You have transaction 1, 2, 3, 4, 5, 6, 7 in each of these ledgers, and you have a magic number. So if you look at the ledger over there in the middle, you have a magic number. Now, what is this magic number? This magic number is the key to our consensus algorithm. And here's how the consensus algorithm for our public ledger works. Okay. So the magic number in our case is the one number, okay, which, if appended to the series of transactions in the ledger above, right, reveals a message which can be transformed by a SHA-256, by a hashing algorithm, by a cryptographic hash algorithm, in this case, a SHA-256, right, to give a digest whose first n digits are all zeros. Okay, so essentially what we have is a way for people to prove that different transactions arrive in different orders. And I'll tell you how. the thing about a cryptographic hash function is it will change the digest if even a single character of the input message gets changed, which means that if the ordering of the transactions in this ledger was changed, the final cryptographic hash digest of this ledger would be way different from what you would get if you were to simply get the digest for this series of transactions. All right. And now the network protocol dictates us to find a separate number. Now, this number has got nothing to do with hashing. This number has got nothing to do with the transactions, their orders, the balance of somebody, the unique transaction ID. It has got nothing to do with those. It is any number. Okay. This magic number is any number which can get appended at the end of the ledger. All right. And then once we find the hash of the entire message, we will get an output whose first n digits are zeros. Now, what is n? N is something which gets defined by the network itself. So in case of Bitcoin, I think it was 40 to begin with. It's gone up ever since, and it keeps going up and down depending on how the network itself wants the transactions to be governed. Okay. Now, the magic number itself is also the proof of work. But here's the critical thing here. Computing the magic number is not computationally easy, right? So there is no way for you to know the number directly from the digest which you would get after hashing that number. Okay, which means that if you wanted to find a digest with the first 30 or 40 odd digits or characters as zeros, right? There would be no way for you to know that this would be the series of transactions which would reveal that. Which means that if you were to find the magic number, you might actually have to start from zero and end up all the way into the billions. So if you want to find this number, you would have to keep doing this all the times. Okay. Now the thing is, we can consider this magic number as the page number for this ledger that we are building. Okay, but there's still something missing because we have this ledger, right? But this ledger cannot again run ad nauseum ad infinitum, right? If you know how to drop entries into a journal, you typically take a journal and you use the pages of it, and then you have a new page and a new page and a new page again. And each page has to get linked to another one, right? That's how a typical book works. What we have here is a series of journals or a series of ledgers, none of which are linked, and we can easily swap the positions of either of these ledgers for one another, and we would still end up with the same problem that we don't know which transactions came first. So let's see how we can solve this problem. Next slide, please. Okay, so the way we solve this problem is by linking every single ledger to the previous one. Okay, so once you found the magic number, which is synonymous for the proof of work, once you found the magic number, you append it, and then you find the hash of the entire ledger for the transactions plus the proof of work. You have the hash of that one single unique instance of the ledger, and then you use it every single time a new entry has to be made. Which, if you look here, the middle ledger uses the previous hash. So this is the previous ledger hash, which is at the header of the new ledger. Okay. Now, this is one way of saying we are building a new journal, and the new page of this journal is continuing from the previous page. And there is no way for you to swap positions between the ledger pages, because this would immediately change the history of every single proceeding transaction after that. And there is also no way for you to change the order of any transaction within each and every single entry, because that too would again change the hash of that unique ledger as well. Now, I think I'll just come to the very obvious fact. Since you can see that the data looks like a series of blocks appended to each other via these linking strings or links or chains. That's also one reason why this unique data structure gets called a blockchain. Okay, so there's no further magic to it. It's essentially a series or a linked list of hashes is what you have here. Okay, so what do we build out of this blockchain? What is it that we can do with this? And is this ever going to add any value to our business? Let's just see. Next slide, please. So, as I was saying, what we built today is a public ledger, and we've arrived at a ledger which used a particular way of ordering transactions. In every single public ledger, or in fact, in any ledger that you might end up using, the first 3 or 4 odd rules of the protocol remain the same. The only thing that ever changes is how you arrive at a consensus on ordering those transactions. The one way of ordering transactions that we've explored here today was proof of work. I've used it because it's the one which is the most popular and probably the earliest way of doing it. But there are others. If you are familiar with systems engineering, if there are any systems guys among you, you've used Kafka in the past. It also is a major component of distributed computing, and it uses a totally different way of arriving at consensus on how different transactions get ordered within the Kafka partitions. If you are from the Ethereum world, you would know that there's a different way of doing it. If any of you use Hyperledger Fabric, which is again a private permission blockchain, there are actually multiple ways in which you can do consensus. So it actually comes with a pluggable consensus. So like I said, you have 3-4 or different rules which are common across the board, but you have consensus which can differ. So Hyperledger Fabric offers you a way of plugging in consensus algorithm according to how you would want to structure your network. So you can actually end up building a totally public network if you want to, using Hyperledger Fabric with a relevant consensus algorithm as well. So yeah, eventually the blockchain that we end up with, or rather the use cases that we end up with, depend entirely on the blockchain that we are using, and the blockchain that we use also sort of governs the use case that we build, and vice versa. So we're just going to focus a bit on some of the business use cases for blockchain before calling a close to the session. Okay, next slide, please. Okay, the one unique thing about blockchains for business, again, is it has to be a shared ledger. We've already seen how a shared ledger works. Participants in the network need to have a shared copy. I think we can probably clarify that problem a bit later once we arrive at the question session. What's more important is obviously privacy, because in enterprise, privacy and security of data are at the heart of every single solution that we end up building. We have to achieve consensus, but we don't want consensus to take a lot of time. The Bitcoin network arrives at consensus every 10 minutes on a new block. We don't really want that if you want to run transactions at thousands of transactions a second. And separately, you also want to find a way to program your network. Okay, so you would want to have self-executing contracts which enable different participants on the network to arrive at SLAs immediately and automatically. So let's just see some of the use cases that we can build out of this. Next slide, please. So this is something that we built for Yes Bank, but this is a pretty tried and tested use case that has been running across the world. So this is trade finance or supply chain financing, if you might want to call it. So what you have is a network of multiple participants. You have manufacturers and you have vendors, and typically a vendor to a manufacturer would want to get paid immediately. But manufacturers are always short of cash and they ask them for a waiting period, right? So they don't pay your invoices immediately. So you always get paid at the end of an invoicing period. But if the vendor really wants access to the cash, they can always go to a bank or any financing entity. They can present an invoice and the bank can then vet those invoices and then check whether somebody else has not financed those invoices already and make a decision on whether they want to finance the vendor or not. Typically, this involves a lot of back and forth of documents. And one major problem still remains in the network, which is again non-repudiation, which means that there's no way for a bank to know whether an invoice has been previously financed by another financing entity. So the only way for them to do this would be to have a network in which you would have multiple financing agents available already, and they would all record transactions, and a bank would only have to look at the ledger and see whether the invoice was financed in the first place or not. And they would easily be able to make a loan assignment there. Separately, this also is a way to trigger auto payments. So you can have a single contract between a buyer and a seller and the financing entity, where a buyer can trigger, or rather the contract itself can trigger payments to either of those entities from an escrow if an SLA is met or remains unmet. So in that case, you would actually end up with a scenario where you would not want a third-party intermediary to program this for you. So supply chain actually is very relevant. So you actually find a lot of relevant use cases in supply chain because of the number of participants, which is pretty large, and the quantum of money involved and the documentation involved as well. So this is a pretty good testing grounds for blockchain. The next slide, please. So smart contracts in themselves are a very unique value proposition of blockchain because they present to you something which was unheard of. If among you, you're familiar with, there are people who are familiar with serverless computing. This was a new paradigm created by Amazon, in which, or rather AWS, in which you wouldn't have to pay for hosting the virtual machines, the containerization, and so on and so forth. The only thing you would have to worry about is building a function and hosting it on a cloud. And the cloud vendor would be responsible for scaling the serverless function on your behalf on the basis of the transactions or the requests that were coming through the network. Now, this comes with a slight problem, because at the end of the day, and if the data is really sensitive, and you have a scenario where there's a single vendor responsible for all your IT, if the vendor khuda na khasta goes down one fine morning, then you would have an automatic internet outage. And this is again very topical, because AWS outages are fairly rare, but whenever they happen, they tend to bring down the entire internet with them. So blockchain offers you, since every single node on the network is effectively a server and has a database, it programs, right? You can essentially write programs and then pipe to the network. So the network then would be responsible for democratically. Okay, next slide, please. Okay, One final, I think we have a use case is that of a distributed asset exchange. It's actually pretty similar to smart contracts in the way that smart contracts enable you to write distributed programs and execute them on the cloud. An asset exchange is pretty similar because an asset can also be programmed, and you can have multiple regulators and issuers and investors for those assets. And this asset can be a bond, it can be a loan security, and this asset can be easily tracked and traced by a regulator if you have those through the network, as payouts are made by the asset issuer. It can separately also be a physical asset. Let's say in a typical supply chain organization where you might be manufacturing something and you want to track and trace the origins of a certain produce or an article, you can do that through a similar asset exchange network. Next, please. So finally, the value proposition of blockchain essentially is portability. Like I said, you would want all the benefits of serverless without having any of the downsides associated with it, right? So the downsides with the serverless are obviously, AWS or Azure can go down any given day, and they would take your entire business within. But in a purely public or or rather a more decentralized distributed network, you would actually have a way to not run your infrastructure, but be able to govern your business network either way and have full control over the data that you end up. I think we've covered the use cases for now. I'll be happy to take any questions.
Thanks, Anusha. Thank you so much. I think that was really very insightful. Really enjoyed the flow in which you did things. I'm going to start with, I think a lot of the questions that came in have kind of been covered also. Like a lot of them were around looking at what kind of use cases you can look at in financial services. We'll come to the career piece in a bit. I think we'll move that to the second part of the discussion. But one quick question that came in was along the lines of public and private blockchains. So while there are a lot of private blockchains, and we've seen a lot of benefit where within an organization, having a private blockchain has various use cases and is easier to implement. When it comes to more public good and initiatives, for example, there was recently an initiative in the news about using a public blockchain for access to untampered documentation for the purpose of, say, lending or NPA management. Or understanding litigation and legal cases against borrowers, where multiple lenders would come together to use such a system. The question that arises is implementability, like who takes ownership, who takes the initiative to set something like this up, who bears the cost. So from a practical perspective, what are your experience been in terms of how do these models work when looking at implementing this technology for something like this?
I'll actually give two instances of blockchain for let's just say the social solidarity sector that might make sense. We've been working with a few large foundations in Europe that want to track and trace the effectiveness of donations that come through their solidarity network. But at the same time, they don't really want to be too transparent as to reveal every single thing, because a lot of donors want to be anonymous, but they also want to have a one-on-one relationship with the foundations that they are working with. Now that's a typical scenario. Again, that's a typical scenario where you have a very small subset of entities who are coming together for a very narrow business purpose. In this case, the purpose being project management of social solidarity projects. That's essentially it. Again, the mechanics of governing the consortium are very important, because that's essentially what defines how a network gets built in the first place, or whether you end up using an existing network. Now, if you want to build a new network, you have to first of all decide whether you want to consume this as a SaaS offering only, in which case this is actually not a distributed offering entirely, because if you are consuming it like any other SaaS offering, the vendor whose offering you end up consuming is effectively the centralized database provider for you. So I think it's a toss-up between whether you can actually host, support, and maintain a server and a database in your own environment versus the ease of use. Now we in the blockchain world, we have a very we actually have uh, our favorite whipping boys in Google and Facebook, and we like to run them down by calling them single centralized and everything. But we also do recognize the ease of using something like Google Sheets or or Google Slides, because we don't have to worry about hosting it on our own. Now compare that with hosting or compare that with a totally open source project that you have to self-manage. You would then actually have to manage your own servers as well and ensure that the service is running at all times. So if you already have the IT infrastructure to do that and you have the experience to do that, I think it makes sense. But if you are a novice as far as this concerns, I think you should be focusing then on building end applications and piggybacking off of an existing SaaS service rather than building one from scratch. In that way, I think public networks win out because they are not held centrally by any single entity, even though there are disputes regarding that as well. But you can just host an application, you can build an application contract, host it on a public network, and that's it. Because nobody can own Ethereum, but you can build an application which leverages Ethereum and again works on top of it. So it depends entirely on the use cases, I guess. Okay, did I just drop the connection?
Hi, can you hear me?
Okay, fine.
So sorry, I think I was just talking on mute. No, thank you for that. I think that your answer to that was very helpful in terms of clarifying private versus public. There was another question on, and this is a specific one to do with the whole point of the protocols for blockchain in terms of there is a need for any transaction to be validated by the members of the blockchain, right? And while we understand the relevance of this mechanism to ensure sanctity of data and acceptance across the entire network, what about the other side of it where it takes up more time? How do you balance that whole trade-off in terms of speed versus sanctity of data?
I think it depends entirely on the implementation. Again, so the devil is always in the details. We can choose to build a service, or we can choose to build an application, and we can choose to build a very powerful application. But the problem is, the more powerful an application becomes, and the more features that it gets to offer, the slower it gets. Okay, it just comes with the domain, right? Because the more validations that you add to a contract, or the more steps that you add to a workflow, the more chances of failure you end up risking. Okay. Secondly, you don't always know whether the different systems in your network have the same chances of failure, and whether they have the same, let's say, latency, or whether their latencies are even in the same time range as well. You might have systems which have a latency of a couple of milliseconds, whereas some might take a few seconds or even multiples of seconds. So the problem is ensuring that you have the right expectation in terms of the speed that you want to expect, and finally the number of validations or business logic that you want to run through the network as well. But having said that, I think there are ways around this as well. So let's say you have a network which experiences a lot of traffic, but your application really has to be compliant, and it can only process, let's say, a few hundred transactions a second, whereas the network traffic is in the thousands of transactions a second. What you would end up with is again, if they were just coupled point to point, the network and your application, the application would fail catastrophically every single time. So in order to stop that from happening or prevent that from happening, we end up installing a buffer between the network and your end application, which is sourcing transactions from the network. So the buffer would asynchronously pipe transactions from the network to your application and ensure that there's always a steady state of transactions per second processed by your application. So that's a very enterprisey way of doing it, and I think it's also a very standard way of doing it as well. It also gives you the freedom of decoupling a lot of business logic from your one single application, and then you can arrive at a more internally distributed way of doing it. So instead of a single core banking system which you would otherwise have, you might end up with a more distributed, a more lightweight set of applications, each of which is specialized to its role, and you have that single buffer which I mentioned. It can be a message queue, it can be streams, it can be anything which asynchronously pipes transactions directly through them. So that's one, like I said, that's an enterprise way of doing it. However, there are blockchains which don't really suffer from the same problems that a lot of public blockchains suffer. For example, the proof of work consensus mechanism that we just discussed actually also has to ensure that transactions are fairly are moving at a fairly laggardly pace. And if you really want to run it in enterprise and at a higher pace, you might want to give up some of the, let's say, rigidness of the protocol for something which is more lightweight and something again which we also see in the private permission world. Hyperledger Fabric does it with Raft, and they are able to do a few thousand transactions every second because of this one assumption that the network is private permissioned, right? So there is always this give and take that you have to end up with. So you either have to have a network which is totally public and totally scalable, then you want something which is totally compliant and totally secure and totally tamper proof. So there are a few give and takes there which you have to end up with.
No, thanks. I think that was really interesting, and also in terms of how you defined it based on the use case. I'm going to switch over to the career side of things. While we did cover a bit of it during the deck, but like one of the typical questions, of course, from students is that what are the career opportunities when you look at, say, a company that specializes in blockchain, right? And looking at the applications of blockchain, which can really be quite vast. So what are the opportunities from a career standpoint, and B, what are the more typical capabilities that a student should try and build to pursue such a career?
Well, a lot of my friends who again come from the enterprise side of things, they when they got into blockchain, they were actually able to take the learnings from enterprise architecture seamlessly into blockchain, because again, the fact about back pressure remains the same whether you are a blockchain engineer or a typical Java engineer. So those problems remain the same. I think there are we actually have better libraries and better SDKs now than we had 3, 4, or even 8 years ago. If you come from a more, let's say, JavaScript background and you want JavaScript everywhere, every single blockchain project that I have seen till date offers very robust support for Node.js and JavaScript, and you can start developing right away. In fact, the tech that we covered today might not even be relevant for a lot of our young friends here, because a lot of the problems of connecting systems in a blockchain network are abstracted away by the SDKs themselves. So the only thing that you might ever want to know about is how does async await work, or how does await work, or how do promises work, or in any single language. So I think it eventually comes down to how good or how capable are you of taking up a new project. But it might actually not be that difficult from or that different from developing a simple 3-tier application eventually. I think it's pretty relevant for me to point out that a lot of blockchain applications that we built, whenever they were in Express, they always ended up consuming an SDK of sorts. If we used Hyperledger Fabric, we ended up using a Node SDK. If we built a Stellar application, we ended up using a Stellar Node SDK anyway. And a lot of the problems of interacting with over the network, over gRPC or protocol buffers, were actually abstracted away by the SDK. And the only thing that the developers had to focus on was the business logic and ensuring that the contracts really did follow the business logic that was sent to them by the business teams. So in that way, or in that sense, if the end goal for you is to become a blockchain application developer, I would say that the journey is not really that different from becoming a typical web application developer. If on the other hand you want to become a core blockchain developer, I think it's the same as becoming a core C++ developer, because you would then directly be working with consensus algorithms, right? Which would really matter, right? So you would have to work on algorithms which would have to know about the time complexity of executing, and also ensuring that stuff really does work on the bare metal. So different goals and different expectations. A lot of the developers that I interact with are looking at a more application developer role. And for them, I think it's actually an easier world out there than it was, like I said, some time ago. And there is good documentation out there in any blockchain ecosystem that you can take up right away and get started with. You might never have to deal with the core fundamentals of how your blockchain runs ever. It's the same thing you do every single time you are developing a banking application as well, right? Not a lot of people know how RTGS works, or how NEFT works, or how IMPS would work, or how any ATM network works. But we have people who have been able to integrate those systems within their payment applications. So I think we have good enough as abstractions of the underlying technology. And if you want to take up some of the blockchains, I think a good way is to start focusing on the front end that you would want to build, and then maybe go deeper from there.
Thank you, Sanjay. Thank you so much. I think that's very helpful. Apologies, but I think we've got to a stage where we'll probably have to wrap things up now, given the time. But again, just want to take this opportunity. I think you've been able to translate a concept that generally tends to be very technical and very not always easy to understand into a space where I think the students have really appreciated. And from some of the comments you've also seen on our chat, that they've really been happy with the session. So kudos to you, and I really thank you for participating today in this session. And also, I think more importantly, for the students getting that sense of what are the career opportunities, what are the kind of skill sets. It's always important to get that perspective from the industry. So really appreciate you taking your time out today.
Thank you for having me, guys. Actually, it was all your presentation. I just filled in with the words. That was basically it.
I'm glad to have you today. Apologies again for the glitches from a technical perspective, but like looking forward to interacting with you in the future. What we usually do also is students tend to start writing into us with more questions. So we do find any questions, we might just pass those on and then create a dialogue between you and the students as well. But otherwise, thank you so much. Have a good evening, and to the students, thank you again for joining in. As we always say, please do reach out to us. You know the email address to reach us at. Please send in your queries. If there's any specific topic you'd like us to talk about, or any way in which you'd like us to run these sessions, we're always happy to hear your thoughts. But otherwise, thank you so much for joining today, and have a good weekend.
Thanks, guys. Bye-bye.
Thank you. Bye-bye.